Okay. Good afternoon, and welcome to the last physics colloquium for this year. Before I introduce the speaker, I have an announcement for the PhD student of the cycle number 40. At the end of the colloquium, after the questions, there will be a QR code on the screen to register your attendance, okay? So please don't leave and be patient until the very end. Okay, now it is my pleasure to introduce Professor Mariangela Lisanti. Mariangela is a faculty member at Princeton University and a research scientist at the Flatiron Institute in New York City. Before the faculty job in Princeton, Mariangela got her undergraduate degree at Harvard University, PhD at Stanford University, and then she was postdoctoral fellow for 3 years at the Center for Theoretical Science in Princeton. As we will hear today, Mariangela tries to answer some of the most fundamental open questions in the universe. And the spectrum of research activity is remarkably broad. And I would say a common theme of her activity is the close connection to experimental data. Okay, this is true whether she tries to understand the smallest length scale in nature from the data of the Large Hadron Collider, or the large scales of our galaxies and beyond, as we will hear today in the colloquium. She's a particle physicist by training, but the research she does is very interdisciplinary, with ideas from astrophysics, computer science, and data science, and many other things, as we will hear today. So the subject of today's colloquium is one of the most urgent open questions in fundamental physics, which is the particle nature of dark matter. So in the last few decades, astronomical and cosmological observations came together to a consistent picture where there must be some unknown form of matter 5 times more abundant than the one we know and we understand. And this form of unknown matter has been dubbed as dark matter. There is a compelling paradigm, it's called the cold dark matter paradigm, and the cold dark matter paradigm has been confirmed spectacularly at the largest cosmological scales that we can probe, but we do not know much about the dark matter properties at smaller length scales, such as the one of our galaxy. This is relevant because it's something we don't know. We could learn something more. And it's very timely because we will be flooded by astrophysical data in the near future that will shed light on some important matter on this regard. I will not say anything more about this because it's the subject of today's colloquium, and we are lucky to have one of the leading experts in the field. Before I stop and leave the floor to you, I would also like to say that Mariangela is a very known and influential figure in the community of particle physics and cosmology, and her work was recognized by several awards. Actually, I know that the first award was back when you were in high school, that during a summer internship at Yale University, she developed some new condensed matter result that gave her the Intel and Siemens Award, and the MIT Technology Review named Mariangela one of the top world's innovator under the age of 35 when she was only 18. And then she didn't disappoint at all the expectations. She got several other awards. The list would be too long. I would just mention a distinguished award from the president of Princeton for teaching, and also the Simon Investigator Award from the Simons Foundation. So thank you very much for accepting our invitation. It's a pleasure to welcome here, and please join me in welcome Professor Mariangela Lisanti.
Thank you very much. Thank you for the very kind introduction, Francesco, and for the invitation to come out to Padua. This is actually my first time in the area, so it's been really wonderful to see the city. I'm going to talk today about some work that my group has been developing. We've been focusing a lot on the question of dark matter. So how can we describe dark matter in terms of its particle physics nature? There's a worldwide effort, experimental and observational effort, to try to get at these questions. A a lot of work going on at the Large Hadron Collider at CERN, a lot of smaller scale experiments that are trying to look for dark matter interactions on Earth. There's a long list of these. One of the things we're working on now, sort of looking towards the future with a lot of the data coming in from some new observatories that are going to be coming online, is using galaxies as essentially laboratories for testing the fundamental particle nature of dark matter. And so my group has been working a lot on building the theory for this, and I'm hoping to kind of give you a little bit of the flavor of the type of work we've been doing over the course of the next hour or so. So the paradigm in the field is that of cold to dark matter, which has been verified on the largest scales of the universe. So this is looking at the structure of galaxies across the cosmic web, so very large scales, looking at data from the cosmic microwave background. All of this is pointing to a picture of the dark matter being non-relativistic, so fairly slow in the early universe, and possibly collisionless, so not interacting with itself. Like any hypothesis in science, we want to make sure that it's validated across all scales. So it's been remarkable the level of precision that we've been able to validate this model on these very large scales. Where we are as a field right now is pushing this down to smaller and smaller scales to see if the theory holds, if anything breaks, if there's new physics that kind of arises when we start considering scales on the size of galaxy clusters or down further to individual galaxies like the Milky Way, or even smaller systems such as dwarf galaxies. What I hope to convince you of is that this is a particularly opportune time to be addressing this question for three primary reasons, essentially coming from advancements on different fronts. So the first is advancements that have been coming from particle physics model building, from the theory community there. And that's been a recognition over the last decade or so that there's just sort of a very general class of dark matter models you can write down that are viable and consistent with known observables. And there's a sort of newfound appreciation that the dark matter itself can take on a wide range of masses, can have a wide range of couplings to the standard model or possibly to within itself. So theoretically, it's just been kind of a burst of creative activity that's really kind of underscored how many different scenarios there are out there that are viable theoretically. Simultaneously to this has been a tremendous amount of advancements going on the astrophysics front in simulating galaxies. So maybe 10, 20 years ago, if we wanted to simulate a Milky Way galaxy, you couldn't even get it to work where you could form a stable stellar disk, which we know exists. The level of advancement there has been rapid. We can now very easily simulate galaxies that look very similar to the Milky Way. They're not perfect replicas, but pretty similar. We get like a stellar disk. There is an example up there in the middle panel. So that's been a huge advancement on the simulation side. And then the last is just the sheer amount of data that's coming online. So we've already had some observatories that have been shedding, opening up new windows. So the Gaia Observatory has been one, which has been mapping the full phase-space distribution for stars, about 1 billion stars in the Milky Way. We have data from DESI. Upcoming would be data from Roman Analysis T. Euclid, JWST. It's just, there's a very long list of observatories, either online or about to come online. We're about to be completely flooded with data. And I'm going to argue we're, on the theory side, in terms of trying to understand all of this in terms of dark matter, we're almost kind of unprepared to handle all of this. It's going to be a very exciting opportunity, and we need to be able to get our theory to a point where we can start comparing to the data and being able to use it to really make robust conclusions about different properties about the dark matter. So for the first part of the talk, I'm going to focus on cold dark matter because it's pretty classic, and it'll give us a base from which to talk about some of the complexities that arise when you want to try to model how dark matter behaves on galaxy scales. And then in the latter half of the talk, we'll start sort of expanding out from there and considering what happens when you start changing the properties of the dark matter particle itself. And so lots of weird things can start occurring there, and so I'll show you some images. So let's start by just thinking about how a galaxy evolves. We have some initial density perturbations in the universe. And in the regions of highest matter density, you start capturing gas in the center of those high dense regions. And those are kind of the initial stages of galaxy formation. Over time, those small galaxies will continue capturing more gas. They'll start forming stars. They'll start merging with each other. So they'll combine, they'll collide, forming even larger galaxies until we end up with systems that resemble what we're used to seeing at present day. In this evolutionary process, the assumptions you make about the dark matter particle have important roles at almost any stage. So for example, the assumption that the dark matter is cold in the early universe is one that says its mean free path is short. So that means that the dark matter will sort of be able to stay in these little halos, and the halos themselves would be reasonably stable. So you'd be able to form these galaxies because you could capture gas. If, in contrast, the dark matter was hot, so it had a very long mean free path, the dark matter could escape from these halos. It would wash out that initial structure. You wouldn't even form those galaxies. If you were to add collisions, so if you would allow the dark matter to collide with itself, it can start changing the picture even at later times, because the dark matter in the centers of these galaxies here could interact with themselves, and that can end up changing the actual properties of the galaxy distributions. So when we talk about small scales, small scale structure, that's a term that I'll probably use throughout the talk. What we're talking about is structure on the scale of a galaxy and also smaller than the scale of the galaxy. So something like the Milky Way would be surrounded by a big halo of dark matter. And the overall density of that halo would be peaked at its center. But there's a lot more structure that's there. And so if you were to put on your dark matter goggles and look at a Milky Way galaxy, you'd see something like this, where there's a lot of sort of these little speckles here, small pockets of really high density of the dark matter. Those are little subhalos. Each one of those is sort of flying around, orbiting around in the galaxy. The largest of those will capture gas and stars, and will themselves be small little dwarf galaxies. And we observe those today. So here's a little cartoon image showing some of the dwarf galaxies that we've discovered in the Milky Way. But then you also have some of these little dark matter halos here that are small enough that they won't capture gas or stars, so they remain completely dark. So they were sort of like a very dark concentration of dark matter that's there. They don't emit any light. The only way that we would be able to detect them is through their gravitational interactions with known matter. So let me kind of give you a sense for what we've been learning recently about structures, small-scale structure within our own galaxy. I'm going to show you a movie that kind of summarizes what we know about the locations of dwarf galaxies and stellar streams as recently gathered by the Gaia satellite. So let me get the movie going. So as we start here, we're going to be zooming in. You'll see little boxes kind of fly by. A little box, like there's one right there, is a location of a dwarf galaxy. These ribbons that you see are stellar streams, so they're very coherent paths for stars. And those stellar streams are formed either by globular clusters that are disrupting as they orbit the Milky Way, or by dwarf galaxies as they're disrupting. So we see that there's this sort of wealth of structure that we're mapping out, and this is only the beginning. So this has already been quite revolutionary from Gaia data alone, but the upcoming Rubin LSST is going to allow us to map this out to much larger distances from where the sun is. And so we'll be able to really expand that map, discover more dwarf galaxies, discover more of these stellar streams. That's within our own Milky Way, but that's only just the beginning, because what we're learning about other galaxies is extending out even beyond the Milky Way. So this is a summary of our current understanding, current amount of data we have for galaxies that are roughly the mass of a Milky Way. So each gray circle is a Milky Way-like galaxy, and the dots inside correspond to the number of little dwarf galaxies that we've discovered in each one of those. So our Milky Way is here, and we've discovered on the order of like 60 dwarf galaxies, so there's 60 little red dots in there. As we go out further, so here's going out to about 20 megaparsecs, we've discovered about 30 other galaxies that look about the same mass as the Milky Way, and each one of those has on average about 10 dwarf galaxies inside of them. So this is coming from data primarily from one of my colleagues at Princeton, Jenny Green, who's led this ELVES collaboration. And I remember meeting up with her one morning for coffee, and she was just sort of offhandedly mentioned that they can measure these really faint dwarf galaxies, and they're getting so many of them, and all of these Milky Way type galaxies that they're finding. And I was just kind of amazed and stunned that we have any kind of level of precision like that to be able to see these systems. And then this year, the SAGA survey published an updated data set. So they are seeing something like 100 Milky Way-like galaxies going out to 40 megaparsecs. This is going a little further out, so the dwarfs inside these Milky Ways are pretty faint, but you can still make out on average about 4 dwarf galaxies per each of these Milky Ways. And then out here, a very large distance, we have data from Sloan. And that's going, that's very far away. So as you can see, we're also gaining this sort of information that's going to allow us to understand how common our own galaxy is within this broader picture. So that if we were to discover something unusual in our own Milky Way, we could then end up saying if it's unusual because we don't understand the physics of what's going on, if the dark matter properties our modeling of the dark matter is incorrect, or if it's unusual based off of sort of the variation, the allowed variation that we see observationally. So when we want to describe the properties of these dwarf galaxies, there's a number of things that we can look at. The simplest is just counting them. So we can count the number of these small dwarfs as a function of their mass. This is sort of roughly the current state within the Milky Way. So here's the mass of the halo, subhalo, and this is the number that we detect. So for reference, the Milky Way itself is about 10 to the 12 solar masses. The dwarf satellites that I showed you some of the images for are here in mass, so they're kind of populating this tail down to 10 to the 10 solar mass. There's a number of techniques that are really starting to become quite sophisticated that can push down to lower mass subhalos. The purple here is showing data that's coming from strong lensing. So this is strong lensing of individual subhalos in other galaxies. And so right now, they can find this down to about 10 to the 9 solar masses, and they can place upper bounds below that. But in the coming decade, the expectation is that they'll be able to actually turn these upper bounds into data points down here. And then the other data that's shown on here in blue is coming from using stellar streams, so those coherent ribbons that I showed you on the earlier slide. The stellar streams can be quite powerful because if you have a dark subhalo that happens to crash through one of those, it can perturb the stellar stream, it can break it in half, and you could look for those breaks. So that could be an indication that it had an interaction with some dark compact type object. So people have been looking for those and using that to set additional constraints. So with both of those techniques, the promise is that we'd be able to really reconstruct these counts down to about 10 to the 7 or 10 to the 6 solar masses. And just for context, everything above roughly 10 to the 8 is probably visible, has some amount of stars in them. Below 10 to the 8, those objects would be completely dark. So we'd be detecting these things down here purely through their gravitational interactions because there's no emit light in any form. For context, the prediction for cold dark matter is shown in black. And then the different color lines are just showing different models, dark matter models. And so you can see that there's a variation in what would be predicted, and that with the upcoming data, we would be able to continue testing whether or not cold dark matter holds going down to this point, or whether or not we've excluded these other models and so forth. The other thing that's relevant, and it's not just counting these subhalos, but also looking at their properties and their internal structure. So one common thing that we look at is just how the mass density is distributed in these subhalos. So we usually show this as dark matter density as a function from the distance. And in cold dark matter, there's a very standard prediction. This density distribution is universal across mass scales, so across different subhalo masses. And it follows what's known as a Navarro-Frank-White profile, which is essentially just a double power law that goes as 1 over r in the center and then 1 over r cubed in the outskirts here. So if we were to summarize this on a plot that looks like this, so this is going to be a cartoon plot I'm going to show again later, so I want to take a minute to introduce it carefully here. What we're interested in is the inner slope of this density there as a function of the galaxies that we're looking at. So the faintest dwarf galaxies, these ultra-faints, which have very few stars in them, would be here. Then we'd go to larger dwarf galaxies until we hit systems that are on the mass of the Milky Way. Your sort of very simple cold dark matter model without any additional baryons or anything like that would predict that that slope is roughly -1, so it just gives you a flat band across all of these systems. So that's a very concrete prediction for the cold dark matter model. Where we want to go from here is asking, since we're going to have all of this data, we want to be able to test cold dark matter. So we want to be able to make predictions for certain observables that are of interest. But a prediction on its own isn't going to be sufficient. What we really need are uncertainties on those predictions. And this has been one of the real challenges in the field up until now. It's been very difficult to be able to obtain uncertainties here so that when you see a discrepancy with your data, you never really know, is it a high sigma discrepancy with the data or a low sigma discrepancy with the data. And it makes it difficult to know whether or not you're seeing something that really deserves attention or some statistical fluctuation. So a lot of the work that we're developing now and the tools that we're developing are aimed at trying to actually be able to put some error bars on this so that we can make much more concrete and robust statements about when we compare with the data. So let me summarize what some of the challenges have been in terms like why this is actually so hard and why we don't have those uncertainties. The first challenge comes from what's called cosmic variance, which is that if you start from the whole Hubble volume and you have your whole cosmic web there, and you just go and you randomly pick a galaxy that has the mass of the Milky Way, and then you randomly pick another galaxy of similar mass, their properties are actually going to end up being quite different. And so the reason is because the local environment of that galaxy is actually very important and can affect how it evolves. So we can't just model a single Milky Way galaxy. We have to model a large subsample in order to be able to get a sense for what the spread of variation would be just from cosmic evolution. So that's one big challenge. Let me skip this. The other big challenge comes from modeling the baryons in the Milky Way. And so this is, let me kind of give you a sense for how this is actually simulated with the caveat that I'm a particle physicist by training. So this is my particle physicist's cartoon version for how this works. There are groups whose sole expertise is on developing and running these simulations. But when we want to simulate how a galaxy evolves, what do we actually put into that simulation? The first component is cold dark matter. So that's kind of the standard. And so we put in particles that could interact with each other gravitationally. But when we put in a particle in the simulation, we're not putting in a fundamental particle. We're putting in clumps of dark matter. So they're probably like 10 to the 4, 10 to the 5 solar mass clumps, because we can't resolve anything that's more fine than that. Then we put in gas, because we know gas has to be there. The gas is modeled as a fluid, so using hydrodynamics, and is allowed to cool. So all of that physics is built in. As the gas cools, it collapses to these really dense regions where stars will ultimately form. So then you get stars that show up in the simulation. And those stars will evolve and eventually explode as supernova. When the supernova go off in the simulation, they inject energy, which ends up impacting how the matter is distributed. One of the big challenges with these simulations is that the physics of how these supernova go off has to be put in by hand. It's not something that emerges from the simulation itself. So that's a big uncertainty when interpreting the results from these kinds of simulations. And it's something that really needs to be taken into account carefully to understand the uncertainties in the predictions that one is making. The way you implement the baryons has a very important role on what happens to the dark matter density. So the presence of those supernova explosions will tend to inject energy, so it sends the dark matter onto higher energy orbits. And effectively ends up coring the distribution, so it moves the dark matter out from the center of the galaxy. So if we return to our little cartoon picture I showed earlier, when you have cold dark matter and you also add in all of these baryonic effects, the impact is going to change the density distribution for these halos, and it will do so in a way that depends on the halo mass. So for the smallest ultra-faint dwarfs, which have very little gas, very few stars in them, there's not going to be a lot of supernova going off, and so the results there aren't really impacted by the presence of the baryons. But as you go to the larger mass dwarfs, you have more supernova explosions that redistribute the matter, creating these cores in the galaxies. And then as you continue marching to more massive systems, what happens is you continue having supernova that are exploding, but the galactic potential is deepening because the system is more massive. And so that ends up preventing that core from actually forming. So this is very much a simple cartoon. The spread, the sort of heuristics are consistent across different simulation codes, but details like where this peak occurs and the spread in this band can vary a lot from simulation to simulation, again, resulting from the assumptions that are kind of put into these codes. So one of the things that we're a new project collaboration that is starting up now out of the Center for Computational Astrophysics at the Flatiron Institute is a project that's called DREAMS, which is an acronym. It's one of these long tortured acronyms, and I don't really remember what it stands for. But the DREAMS project, the goal of that is to create the largest ever suite of simulations of galaxies that allow us to actually vary over all of the uncertainties that go into that modeling so that we can actually obtain really robust predictions for observables. And so for a long time, it just wasn't clear whether or not we could even generate this number of simulations. The sort of standard in the field is that you have suites of maybe tens of these simulations. They're very computationally expensive. They take a long time to run. And what we needed to be able to do this was something on the order of thousands. So we needed to go from tens to thousands. And the work that was led by Jonah Rose, who's currently a postdoc at Princeton and at the Center for Computational Astrophysics, he demonstrated that this is indeed actually feasible. So let me show you the results of the first simulations that he ran that demonstrate we can actually do this. So it's going to start in the middle. Zooming in on one galaxy as it's forming. This is a galaxy that's roughly the mass of the Milky Way. And what you see are the stars in the simulation coming in. They're going to form a disk. It's going to become more apparent in a second. For this particular galaxy that's simulated, we randomly selected properties of in the baryonic model. We also, this is a warm dark matter simulation, so we randomly selected the mass of the warm dark matter. And we get something that looks roughly like a Milky Way, which is great. That's kind of the state of the art up until now. But what Jonah is able to do is then repeat this process. Each time he picked another random galaxy, different sets of parameters, and kept this going over 1,000 times. So each one of these here is a different Milky Way galaxy that was simulated with different sets of assumptions, both on the baryonic physics and the dark matter physics. They're all still running and turning, which I'm not sure if you can see on the screen. You can also tell just by squinting that the morphology of the galaxies can be there's a lot of variation there. That's precisely what we want to be able to quantify, because those changes in the morphology there are coming from changes in the assumptions about how those galaxies formed. And so we can actually capture that now that we have these really large suites. So this is ongoing work, and we're really quite excited about it. It's we're now about to complete a new suite of cold dark matter simulations. So this is for Milky Way objects. So we're hoping to release that data in the first half of next year. And we're also gearing up to run over 2,000 simulations of dwarf galaxies, also for cold dark matter. Those are going to get submitted, and they'll probably take about a year to run in total. So probably this time next year, they'll be done. I don't like thinking about what this does to our carbon imprint, but for the good of science, we're proceeding onwards. Okay, so that's sort of a general overview of assuming cold dark matter. So now let's start talking about what happens if we go in as particle physicists and start actually changing up this dark matter model. And so just as a reminder of what the goal here is, what we want to be able to do is build up a framework that lets us go from a dark matter model to a prediction for the data. And a lot of the pipeline you need to be able to do this doesn't currently exist. So fundamentally, as a particle physicist, I want to know that if I write down a Lagrangian for my dark matter theory, I want to be able to have some intuition for how that ends up translating into what my galaxy should look like. But at this stage, I could maybe only do that for a couple special cases. And so we really need to build up all of the theory that's needed to bridge that gap. So to do that, a critical element is to actually develop simulations that implement these different dark matter models so we can see how the galaxy forms when you actually change the particle physics assumptions. This is a lot of tool building because a lot of this just doesn't exist. And so there's a lot of hard work that's needed just to get from here to there. Once you have the simulations, you need to turn them into mock observational data that you can actually compare with the data that's going to be coming from these observatories. So that's an important step that needs to be treated carefully. And then once you have that, then you're finally at a point where you can go in, compare the data, be able to say my dark matter model is ruled in, or it's ruled out, or I've discovered something new, or not. As a field, where are we? We're kind of somewhere here. Partly, we still need to kind of understand what all the relevant dark matter models are that we need to be thinking about for these systems. And we have a lot of work to do in terms of implementing this into the simulations. So we're somewhere here, but we're really developing this quite actively. So hopefully, we're kind of on target to continue progressing in this direction to ultimately kind of catch up to where the data is going to be. This is a scenario that I would argue that the data is sort of far ahead of where the theory is, and there's kind of a lot of catching up on the theory side in order to be able to interpret it. So when it comes to choosing which dark matter model to think about, there's a number of options. We usually, or the way I like to think about it is we have the standard model of particle physics, and then we allow new physics there that can explain the dark matter, and perhaps that's by having new particles, maybe one new dark matter particle, maybe more. So that would be indicated by this. Maybe we also add new dark forces to our theory. So maybe there's other force carriers here. And then it can be that all that new dark physics we add, maybe it's allowed to talk to the standard model through interactions, or it can also be that it can only interact via gravity. Either of those is viable. So for the examples that I'm going to focus on for the remainder of the talk, I'm going to consider the case where there's nothing here except gravity. So the dark matter is only gravitationally interacting, which is sometimes actually referred to as the nightmare scenario, because that pretty much means that you have no shot of being able to detect it in a laboratory experiment. And if that's the case, then this is pretty much your only hope for being able to ever detect it. And additionally, we're going to ask, is the dark matter allowed to interact with itself? And if it is allowed to interact with itself, is that elastic? Or is it inelastic? And by inelastic, meaning that in those interactions, can the dark matter actually lose energy? So for the elastic self-interactions, the sort of toy model that we consider is one where there's a new dark mediator particle that can mediate this interaction between two dark matters. And so this would be some self-scattering that's described by a Yukawa potential in the non-relativistic limit. There's a lot of beautiful physics that falls out of this. So when you allow the dark matter to start being able to interact with itself, it essentially is going to dramatically change what happens inside of your dark matter halo. And that's because the self-interactions will change, will actually allow heat to flow in the halo, which is something that you don't have when you have regular cold dark matter. So the process, which is really quite beautiful and simple, is you start off with your dark matter halo, and originally it's hotter on the outside than it is on the inside. So if you have these self-interactions, the heat flows inwards. So you end up heating up the inner part of your dark matter halo. And as you do that, you put your dark matter there on these more energetic orbits, and so you end up forming a core in the center of your galactic system. And that you can actually model this explicitly. It's sort of just an isothermal core that forms there. That system is not stable in that at a certain point in time, you will end up heating the center to such a degree relative to the outskirts that the heat is going to change the direction. So later in time, the heat flow changes direction and starts moving back out. And then some really weird stuff can start happening. Think about, in this case, I've got two dark matter particles here. They scatter off of each other. One of them falls towards the center of the galaxy. Gravity, it has a negative specific heat. So as I fall towards the center, I actually increase the temperature of that dark matter particle. The other one gets kicked out to the edges of my halo. That's kind of like a big, massive heat bath. And so changing the temperature of the outskirts happens very, very slowly. So I have this scattering event. One dark matter particle falls in, its temperature increases. The other one goes out, but barely changes the temperature of the outskirts of that halo. That process continues, and what ends up happening is the dark matter that's in the center, you end up heating a small core, very dense core of dark matter near the center, and its density rises very quickly. It's a runaway process. Eventually, if you let this system run all the way to completion, the whole halo would collapse and just form a black hole. This is actually very well-known physics because it's known to occur in globular clusters. In a globular cluster system, it's the stars that are interacting with each other. But the globular cluster never ends up reaching a point where it collapses to a black hole because eventually the stars end up forming binaries, and that halts this runaway process. But for this self-interacting dark matter model, you wouldn't form these binaries. The process would just run its way to completion. You'd form black holes. So whether or not the black hole formation would actually be relevant is obviously going to be dependent on the time scale at which this would occur. So in work that was led by postdoc Oren Sloan, who's about to start a faculty position in Tel Aviv. So Oren mapped out for a given self-interacting dark matter model what regions of that space were allowed or not allowed. So these two axes here are just describing certain elements about the cross-section for these systems. So this is cross-section for interaction and the velocity scale where the interactions are important. And the shaded regions are excluded by current data. And one of the important conclusions from Oren's work is demonstrating that in the allowed region that remains, that's the region where this gravothermal collapse process has to be occurring. So we know that if you have these interactions going on in reality, gravothermal collapse is going to be occurring for the densest dwarf galaxies we see in the Milky Way. And that's going to dramatically affect, in ways that we're still trying to understand, because this is very much open territory, the density of these dwarf galaxies. So as illustrated here very schematically, let's say in cold dark matter, you predict a distribution for those central densities that looks like this. For some models where the dark matter can self-interact, if you only form those sort of big cores, you would expect lower central densities for those dwarf galaxies. But if you live in regimes where you also have this gravothermal collapse process occurring, then you'd have very different distributions, some of which are going to be very, very dense. And so some of the stuff that we're trying to figure out now is actually exactly what this probability distribution looks like in reality for different models so that we can compare with data. But again, just to kind of underscore, all of this physics is coming out from the fact that the self-interactions now turn on sort of the allow for heat to flow in your halo, which is a very different physics mechanism of what's going on there compared to just the cold dark matter case. And then in the last bit of time, I'll talk about a completely new scenario that we've been exploring, where there's still the dark matter can interact with itself, but now in those interactions, it's allowed, it can lose energy. So this would be like inelastic interactions. This will open up lots of really weird stuff that can start happening. And you can kind of get a sense of that by just starting by thinking about the virial theorem. So why do we even form a dark matter halo? Why is it stable? That comes from the virial theorem. So that gravitational collapse is going to occur until you hit virialization, where you have twice the kinetic energy is about equivalent to minus the potential energy. And when you hit that point, your halo stabilizes, and so you sort of maintain that structure. But if your dark matter can lose energy through its interactions, you add a dissipation term in your virial theorem, and that essentially means that it sort of breaks this virialization process. And so instead, the fact that energy is being dissipated means that your halo can just continue collapsing. And as it collapses, it can form all sorts of weird structures. So maybe it fragments into really dense clumps, or maybe, like in regular baryons, it collapses to form a rotating dark matter disk. This is sort of a dynamics in the dark matter sector that hasn't really been carefully understood, because implementing this in the simulations has never been possible until now. So a lot of this has been very much open questions in terms of what actually happens if you allow the dark matter to start exhibiting all of these interesting properties. To study this, what we did was we worked with a very simple toy model, which is very easy to understand. So it's called the atomic dark matter. So we assume that the dark matter consists of essentially copies of standard model states. So we have a dark electron, a dark proton, and a dark electromagnetism. And just to emphasize, there is no dark QCD in this theory. So this dark proton is itself a fundamental particle. It's not a composite particle. But as in the standard model, with this setup, you can form dark hydrogen. And that dark hydrogen will cool. And you can calculate the rate of it cooling. So this was a nice toy example for us to start off with, just because there's a lot of analogy and intuition that we can bring just from regular standard model physics. The model itself was sort of introduced by David Kaplan and his collaborators in 2009, where they were assuming that all of the dark matter was in this form. In later iterations, so in work by Gigi Fan, Matt Rees, and Lisa Randall, they considered scenarios that they called double disk dark matter, where only a small fraction of the dark matter was in this form and the rest was cold dark matter. So the way in which this dark gas cools is what, where all of the interesting physics is going to be embedded. So just to kind of remind you of what this looks like for the standard model, if we have temperature here on the x-axis and then the cooling rate on the y-axis, for regular standard model, the cooling rate looks like this. And there's a variety of mechanisms that are feeding into that. So this first peak here comes from collisional excitation of hydrogen. Then that second peak comes from collisional excitation of helium. And then this slow rise here comes from Bremsstrahlung. So essentially all the physics that kind of governs collapse of gas, of regular baryonic gas in the Milky Way is kind of embedded in this cooling curve for the standard model. Now, if we did something like this similar for the atomic dark matter, we would still have collisional excitation of our dark hydrogen. We would still have dark Bremsstrahlung, but we wouldn't have this peak because we don't form any helium in this system. We only have dark hydrogen. So in order to simulate this, we needed to do a lot of hard work to develop code to do this. And this was led by my graduate student, Sandeep Roy. The standard code packages that are available, Gizmo is one of these, allow you to put in cold dark matter and allow you to put in baryon physics, but that's it. So we needed to develop a module that allowed us to add in this new dark matter component. This was the first time anybody tried creating a simulation that had more than one dark matter particle in it. And additionally, the first time anyone could run something where the other dark matter component had these really strong energy losses. So just to kind of come back to our cartoon from earlier in the talk, these are the standard elements that go into these simulations, cold dark matter and gas. And what Sandeep did was to add another component of dark matter that itself acted like a gas. So this is the atomic dark matter. It was allowed to cool, where those cooling rates came from actually calculating cooling rate formulae, like that's the particle physics element, kind of goes into that. And then the atomic dark matter can collapse and form really dense regions. Now, we can't resolve that collapse to the final state. So we have to kind of stop after a certain point. So all we can do is sort of track that collapse down to these clumps that are around 10 to the 4th solar masses. In reality, those clumps are probably locations of black holes that would form. But we can't actually track the simulations down that far. So what did we find in running these? So I'll end by showing you the results. So for comparison, I'm going to show you 3 different cases. The left column is going to be a simulation we run that only had cold dark matter. So that's sort of very standard. That's essentially what people had already done. And then the middle and right columns will be scenarios where we add onto that a little bit of atomic dark matter, only 5%. So 95% of the dark matter here is cold, and then the other 5% is in this weird atomic dark matter component. So these pink density plots at the top are showing, after we run these simulations, we run them all the way to the end, we look at where the cold dark matter ends up at redshift 0, present day, and we see the sort of characteristic halo that forms with a little bit of like some little dwarf galaxies flying around. And in all cases, that all looks roughly the same. So the cold dark matter does what you'd expect the cold dark matter to do, which is good. Where the weird stuff starts happening is when we look at what happens to the atomic dark matter in each of these. So remember, again, the atomic dark matter is allowed to dissipate energy, so it loses energy. What we find is that it collapses, and it collapses and forms rotating disks in the center of the galaxies, where these disks are purely dark matter disks. So think about in baryons, right, regular regular baryons, you form a rotating gas disk and you get a stellar disk. This is saying that if you had this component of dark matter, you'd get a corresponding dark matter disk that would be aligned with the stellar disk in the Milky Way. The sizes of the disks here are different because we've changed the cooling rates of the atomic dark matter between these two models, so that kind of gives you a sense for how the cooling rate alters the final phenomenology. The other thing that's important is the fact that these disks here are not stable. So unlike with baryons, these disks ultimately end up fragmenting. They break apart into these really dense clumps. So these dark compact objects, and those dark compact objects are shown here. They all end up being concentrated near the center of the galaxy. So there's a lot of really interesting structure that emerges by just adding in these dissipation mechanisms in the dark matter sector. And the corresponding result here ends up having a really big impact on what happens to the baryons in the Milky Way. So this is showing for those same 3 simulations what the baryonic gas and stars end up looking like. And what you can see by eye is that in the scenario, especially this one here, where we add in a small amount of atomic dark matter, we essentially just don't form a disk of gas or stars that is anywhere comparable to what we'd expect to get for the Milky Way. So this is sort of what you'd want it to look like here. And in general, my general rule of thumb is that in astrophysics, if you can see it by eye, that means it's probably ruled out. So this way, you could sort of see by eye. This is, you know, this parameter point is definitely, we broke our Milky Way there. This doesn't work. And intuitively, you can actually understand this as possible, as follows. The atomic dark matter is only a very small fraction of all of the dark matter. It's only 5%. But if you take 5% of all of the dark matter and then collapse it down to the center of the galaxy, the total mass you've just collapsed it down there to is about equivalent to the total mass that's in baryons. So for that reason, even though you put a really tiny amount of weird dark matter into your system, you can actually have really dramatic imprints on what happens to your galaxy as a whole. So that was something that really surprised us when we ran these simulations. We didn't think that we were going to be very sensitive to the addition of this one dark matter particle. And what we ended up learning from this is that it's actually really easy to break a galaxy by changing the properties of the dark matter even just a little bit. So galaxies as a whole are very sensitive to the particle physics assumptions about what you're putting into that dark matter model. And that really motivates us on the particle physics side to think really carefully about the models that we're writing down and think about whether or not they're allowed based off of what they would do to the galaxy. Or separately, perhaps they're highly discoverable through the imprints that they would leave on the galaxy. So with that, I'll just end by acknowledging my group, so my graduate students and postdocs. I wasn't able to highlight all of their work in my talk today, but all of the conversations that we have and their feedback has definitely contributed to a lot of the ideas that I shared with you today. And so just to summarize, I hope I've been able to convince you that in thinking about broad dark sector physics, different kinds of interactions in the dark matter model can lead to really rich phenomenology on galactic scales. And I hope I was able to illustrate this for you in the case of elastic and inelastic self-interactions, but we're going to, our group and our collaborations are continuing to think about other models and continuing to develop all the requisite theory, the simulations that are needed for us to ultimately build the intuition that will let us go from a dark matter Lagrangian to an observable that we can compare with data and use it to test whether or not that dark matter model exists, is the correct model of the universe or not. So I'll end there, and I'm happy to take any questions you have on this. Thank you.
Thank you very much, Mariangela, and we are ready to take questions from the audience.
Okay, so first of all, thank you very much for this informative and stimulating talk. Just a question, as a particle physicist, you know, from my cosmologist friends tell me from time to time that pure cold dark matter has problems. One is what you mentioned, this Caspi behavior. Another, if I understood correctly, is the presence of proto-galaxies, or better, the fact that we should observe more proto-galaxies. So from time to time, they tell me, well, it would be good to have a mixing with some amount of warm dark matter to improve the situation. Now, you introduced elastic and inelastic dark matter interactions. I was wondering, how about having a warm dark matter component? Because the situation is it similar to this kind of self-interacting dark matter, or are there distinctive features?
Yeah, that's a great question. And the fact that I didn't talk about it in detail is not because it's not interesting, it was just more a matter of time. But I did skip over a slide that can actually answer at least part of your question. But where warm dark matter probably leaves its largest imprint is just on the number of galaxies that you'd expect to find, like a number of small dwarf galaxies that you'd expect to find and their mass distribution. So this is actually from one of our simulations where we vary over the warm dark matter mass and just count these dwarf galaxies. And so you can see that as the warm dark matter mass gets larger, which is moving in the direction where it acts more like cold dark matter, you change the total number of dwarf galaxies that you'd expect to see in your system. And the current constraints on warm dark matter are roughly around, I mean, it varies a little bit depending on the probe, but currently it's sort of roughly between 5 and 8 keV, so where everything below this is thought to be excluded. But the range above it is certainly allowed, and exactly where that cutoff is kind of up for debate. The fact that we're getting to a point where we can really kind of count the number of dwarf galaxies that we have in the Milky Way, that's been one of the most constraining observations. Also strong lensing, where we're counting the dwarf galaxies around other systems. Both of those should actually be really quite strong probes of warm dark matter in the coming years. Yeah.
So less than 5 keV would be forbidden?
Yeah, I mean, it's a rough thing because it sort of depends on which, there's just a little bit of a debate in the community, but roughly around 5 kV, 8 kV, below that, it comes in tension with like Lyman alpha observations, also with the current data we have on Milky Way dwarfs. So there are a variety of constraints that seem to be excluding that for the time being. But the data is also going to continue getting a lot better. So this is something that's definitely like high target. We will hopefully be able to rule in, rule out pretty soon. Yeah.
Okay. Any other question? Especially from students, don't be shy. Okay, you're not a student, but that's okay. You make me work.
Hi, thank you for the nice presentation. I was wondering about this passage of dark subhalos through stellar streams. These are very interesting. I work for CTA and MAGIC, so that would be really good for us to observe, but we need to know where they are. So do you have any idea in the next 10 years if we will be able to tell how many are in our galaxy and where they are?
I mean, the hope is yes. There's already one possible detection. So actually, very soon after Gaia had one of their big data releases, people looked at this stellar stream that's called GD1. and noticed that it had a break in it. And you can potentially explain that break as coming from one of these dark subhalos. The dark subhalo, so people then did the exercise of trying to figure out where that dark subhalo would be. They couldn't find it like through other ways. So I mean, so there's some predictions about like what orbit it would need to be on. And it also, people aren't 100% certain that like it actually is a dark subhalo. But that's essentially kind of like the tip of the iceberg, right? It's like the first possible detection. The hope is that with Rubin LSST, when that turns on, we'll hopefully have like a bunch more of these breaks. And then that would tell us something about the statistical population of the dark subhalos that would exist in the Milky Way. My guess is that reconstructing the location of any single one of those subhalos would probably be extraordinarily difficult. Probably not the first thing that one would be able to do, but you could make predictions for like how many of these things are out there and whether or not that's consistent with cold dark matter or not. So I imagine for CTA, knowing the precise location would be the most useful thing. I mean, I wouldn't rule it out because one might be able to kind of backtrack it depending on the particular scenario, but I do think that it is a bit challenging.
Okay. Any other last question? Yes.
Hi. My question is about the hydrogen that they're formed from like dark matter particles.
Yeah.
And I wondered, since like how are they formed, since we don't have like the QCD in the dark matter field?
Yeah, that's a great question. So we assume that the proton is essentially just a fundamental positively charged state. And so then the bound states occurring between a positively charged proton particle and a negatively charged particle, and there's a dark electromagnetism that's keeping them in the bound state. So if you want, you can just think of it, if you prefer not to think of it as a proton, you could just think of it as I've got a new positively charged particle of some mass, a new negatively charged one, and they're being held in this bound state by like an electromagnetic force. Yeah.
Do you need a mass hierarchy between the two, like in the hydrogen, in our hydrogen?
Yeah, that's a great question. So at the moment, everything we've modeled has been with a mass hierarchy. Partly that's because in order to calculate the cooling rates, the way that one does it is based off of the standard model cooling rates and extrapolates. But there's actually a lot of really interesting theory on how to do that from scratch, like calculate the cooling rates even when you're far away from the standard model values. Yeah, we're working actually with an an AMO theorist who is actually very excited about this because he's like, oh, I get to change the fine structure constant and the electron mass, and I get all sorts of things that I'm not allowed to do in the standard model. So.
Very good. Okay, any other last question?
My question was about while simulating these galaxies through different types of models, as we moved from cold dark matter to, say, warm dark matter or atomic dark matter, these models, are we moving also away from the spherical top hat model that we check, or for a warm case, we're going to the pancake model that we expect?
You mean for the actual collapse process?
The collapse process, yeah.
Yeah, that's a great question. I think we don't really know quite yet. Partly because we're only starting to be able to simulate these, and so with the tools that we're developing, we'll be able to go back and kind of double check that against the analytic assumptions that we've been making up until this point. But we're only just starting to be able to run these simulations, so we're not quite there, but that's exactly the kinds of things that we're going to want to be verifying as we move forward.
Okay. Any other last question? Give priority to students, so I run back.
Thank you, and thank you so much for the speech. So in a previous colloquium, we had a colloquium about gravitational waves, And there also was this like issue, let's say, with new data. And they told us that in the near future, we are going to have like a really huge amount of astronomical data also from new interferometers. And will be able to probe a completely new spectrum of gravitational waves events here on Earth. So my question is, when you mention like new telescope and new arrays for detecting these dark matter effects, will those include also some gravitational wave effects or stuff like that?
Yeah, I mean, I think that's a really exciting new direction, an observational probe. And for some of these dark matter models, especially like this one here, where you collapse and you're forming like dark compact objects, there is actually a very strong possibility it could end up impacting gravitational waves. I mean, like, we've not studied this in great detail yet. It's sort of on our long list of things to get to. But like, because a lot of the effects that you have here are purely through gravity, like there might be something really interesting to do using gravitational waves. So that's something that we definitely want to explore, especially given how amazing these future probes are going to be.
So it's going to be probably like the first way to directly observe the gravitational effect and not indirectly through lensing, for example.
Yeah, that would be, if you could see it that way, it would be pretty amazing. Yeah. Yeah.
Okay. Last chance to ask a question. Okay. Okay, so if there is no more question, let's thank Mariangela again.